Hello and welcome to Build Your Own CPU Part 15. In this episode we'll be going through the actual Noughts and Crosses program that runs on the CPU. So this is written in the CPU's assembly language. So if we just start with the beginning of the source code. So this is for private use again, no commercial use. Now here's some definitions just to give you an idea of what's going on. Here we've got A, B, C, D, E, F, G, H, I. That's think of that as the grid for the Noughts and Crosses. Now the memory allocations for the CPU is we've got memory 0 is the ROM page that we're going to jump to. We don't need a RAM page, so we're just using the ROM page. Then we've got the memory here, these 8 bytes of memory from 1 to 8 is for storing the actual data for the Noughts and Crosses. And it uses various bits in each byte to represent where an auto cross has been put. So if we look at the memory layout over here, you can see we've got byte 241. That's the first memory address, that's memory address 1. And this will be bit 7, bit 6. You may recognise this from a previous video, although in the previous video I've got the colours back to front. It doesn't really matter, I just coloured these in the same colour as they come up on the actual screen. Green is the CPU and the red is the player. So if you just look at the first byte here, there's 8 ways to win in Noughts and Crosses. There's going straight across on the first row, straight across on the second, straight across on the third. Then you've got 3 vertical ways to win and 2 going either way across. So that's 8 possible ways of winning. So we use 8 bytes. Now the first bit here, bit 0, will be square C for the CPU. Or if you're the player, you'll get the third bit, which is equivalent to an 8. And B here for the CPU, which is bit 2. And the same again for the player, which will have a 16. So you've got 1, 2 and 4, 8, 16 and 32. So if there's a 4 there, the CPU has got square A. If there's a 32, then the player has got square A. So the reason of having 8 like this is so that I can check that way to see if there's a win, that way, then that one, that one, that one, that one, and that one. I just need to do 8 checks to see whether there's a CPU win, which will be a 7, or a player 1 win, which will be a 56. Just add these bits up. You will never get like the C square turned on both of them, because when the game is playing, it checks the square hasn't actually been used. So it stops you from doing that. So here's the memory layout here. On the left again, A, B, C, D, E, F, G, H, I. Then you've got A, D, G, which is this one coming down here. So that's going across. Then B, E, H, B, E, H, C, F, I, C, F, I, A, E, I, which is that one, A, E, I, and C, E, G, which is C, E, G. All the ways you can possibly win. And when we're displaying this, we only need to look at these squares here because that contains all the information we need, which again was shown in the previous video. Now the next 3 bytes of memory, 9, 10, 11, they're to do with addresses to jump to for when you're actually doing a square. When you're doing the tests, we'll come across those later. And then here's the 4 possible I/O that you can use. I/O 0 is the ROM page we go to. Although we've got one page here, this is where you just save it in the RAM and then this gets written into there to actually switch the page. There's I/O 1 is a RAM page if you ever used it. We don't use it in this program. We managed to do it all in just 12 bytes of RAM. And then I/O 2 is the keyboard buffer. So the motherboard is scanning the keyboard and putting a number in there that depends on whatever key has been pressed. Then I/O 3 is for the random number generator. So we'll have a number between 1 and 9 in there. If we pop back to this one over this side. So here's the actual bytes laid out. A, B, C in order for the first three, and then the next ones are in the order. These are the vertical lines, and then these are the diagonal lines. Now, this is the block diagram of how the CPU works. First of all, who's going to play first? So you'll be pressing a key, star for the CPU to go first, and a 0 for the player to go first. So if the CPU is going first, you'll come down here and it will look for a winning move. And this is all done on page 1 of the ROM. If it finds a winning move, it will decide where to put it, and it then places the cross. It uses page 3 to place the cross. The cross has to be in 3 or 4 places, depending. If, say, it picked A, you would have to put it there, and there, and there. If it picks A and E, it will need to be there, 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 and there. So we'd have to do 4 rights. We'll see that in the code. So it can find a winning place, it puts the cross in there. The program will then test to see if it's won. If it hasn't won, it just swaps over to the player side. If it can't find a win, it then look for a block, see if it needs to block the player from winning. If it finds a block, it'll work out which square to go in, and again, place the cross there and test for a win again. That's just the route through the software. It just makes it easier. Doesn't see any blocks. It will then go, well, what's be the best move? Well, the best move would be in a line with one of his own crosses. So it will try and find one of those. If it finds one, again, it will place the cross into place and pass that control over to the player. If you can't find a best move, as in it's right at the beginning of the game and there's nothing there to check against, it'll want to pick a random place to go. And it'll find a square that it can go in, and it will then place a cross and go forwards. This part here is sometimes if you was right at the end of the game and it was the CPU's turn, you could be in a stalemate condition where all the squares are taken and then you'd be stuck. But what happens is you can see there's a stalemate and it will go back to restart, which is basically coming in the top here again, waiting for you to press a key to who's going to play. On the player's side, be it coming in from here or from the beginning, it scans the keyboard and it waits for you to select a square to go to. It will then check that that square is available. If it's not, it will just keep scanning. If it is available, it will place the naught in that square, and then it will test. When it says test for lose, that's from the CPU's point of view. So it's going to test to see whether the CPU's lost. If it has, comes down here, player's won, and then goes back to the restart again for it to clear the board when you select. If the player hasn't won, the control gets passed back to the CPU. So the CPU runs through its code again and just keeps switching backwards and forwards between them until you come out of one of these 3 at the bottom. Either is a stalemate, CPU's won, or the player has won. And those 3, as I say, come back to the first here. And when you select who's going to play, it'll clear the board and start again. It all sounds quite simple and straightforward. Well, it is. The code's a bit long-winded because I've got a bit of a restriction in the different commands I can use in addressing modes. Alright, let's start at the beginning of the code. So starting on page 0. Who's going to play first? Well, the first thing it does actually in page 0, apart from try and jump to a page, is it clears all the display down, clears all the variables and everything, clears the keyboard buffer, and then it starts scanning the keyboard. You remember, you recognise this from the previous episode where we were simulating the CPU. It goes round and around here. Well, once it's detected you've got something there, it's going to see what it is. Is it a star, which is a number 11 in the keyboard? So it's moving what's in the keyboard into register 2. You can move register 2 into register 1 because we're going to do a bit of destructive testing. It subtracts 11 from it, and if it's got a 0, as in it is in 11, it will skip over here because that's the CPU's go. When it says my go, it's in reference to the CPU, so it's the CPU's go. Go to page 1. So my go down here is move 1 into RAM address 240, the first place, branch to the start, and that will jump straight to page 1. And then we'll carry on from memory address 3 on page 1. This one down here. If it's 11, it skips to 0. If it's not 0, as in it's still positive or negative, then we've got test for another one. So it branched down here, moves the R2 back to R1 because we'd damaged R1, so we collect the original scanning again, put it into R1, subtract a 12 from it. Is it 0? The 0 key sends back a number 12. If we've got a 0, then we skip down here, it must be your go. So come down here, as in the player's go, and that goes to page 5. If it's none of those, it just branches to scan again. Use back up here and reads the keyboard again. It just keeps reading the keyboard until it gets either a star or a 0. And that's this CPU or player. So if we start with CPU, move 1 into 240, branch to start, so that skips us onto page 1. So here we are on page 1. Of course, we'll be coming straight in here at address 3 because we've already done these commands up here, and it's not until this command actually finishes that we switch to this page, and the program counter will be looking at memory address 3. So what we're going to do is find the value that's in RAM address 241. So if we scroll this back up, that's this one here. That's that line there. Going to move that into R1. Now here's a little sort of a fudge around the system. I haven't got any subroutines. I can't call and return. There's no call return command in this CPU yet. So what we do is we move this memory location, which is there, this label, move that into R2. And that's going to be our return address. So if the place where we're going to branch to just here fails, we're going to come back here. Well, we're going to come back here actually. So we've got the return address there. So it'll have a branch R2 when we fail, and that'll come straight back here and carry on with the code there. So we load up our return address. Now here, do A, do B, and do C, they're labels as well. They're addresses of somewhere in the code, and we're going to save them into memory address 249, 250, and 251. That was these ones here. So that holds the address of where to jump to in code. We'll be using it quite a bit. So we're going to branch to the test. So we want to test the first line. So here's test. Subtract 3 from R1. R1 is the number that's sitting in here. If there's a 3 in there, that means bit 2 and bit 1 are both set for the CPU. We've got 2 green ones there. Going here would be a winning line. We're doing a test for a win here. Subtract a 3. If it's a 0, then that's true. So we skip over to this bit here. You branch to do A. Now it's 249. That's what we set just here. Do A address is in 249. If it's correct, we need to do the A, which is at 249. So we branch to, there we go, do A is there. So we're going to do this bit of code here. We're going to move a number 1 into R1. It says we're going to do the very first square, because these squares, not only is it A, B, C, D, E, F, G, H, and I, it's also 1, 2, 3, 4, 5, 6, 7, 8, and 9 in the code here. I can't put an A into R1, but I can put a 1 in there. So I'll put a 1 into R1, then branch to page 3. Now, what it's doing here, this bit here, I've set where I want to go. I want to go in square 1, which is coming across here, place the cross there, which is on page 3. That code, go through there shortly. And then it'll do a test for win. Obviously, the first code, that's not going to happen. Go back here. If the test here had failed, we'd branch to what's called next 5. It's just there. I only called it that because it's looking for a number 5. We've already subtracted 3, so I'm subtracting another 2, so that's a 5 taken away from R1 in total. If it's a 0, then 1 and 4 set, which is 1 and 4 set, and this one's not set. So we'll say branch to 250, which we'd set back here. 250 was do B, which means branch to do B, which come down here, which will put a number 2 in R1 and go to page 3 to set it. So do square number 2. And if that fails, it'll come through and it'll subtract another 1 from it. So it's taken 3, 4, 5, 6. It's taken the number 6 away from whatever's sitting in here. Well, if 4 and 2 are on, it's this one and this one, it leaves that one empty. So we're going to branch to C, 251. We'll have the address of do C in it. It may seem a bit odd at the moment, but it will come clear when I explain the next bit. So it'll jump down to do C, which means put a number 3 in R1 and fill square 3 in, which C and 3 are the same square. Then go off and test it. So that's how it can find a winning line in that row there. And that's just the row. There's 8 ways we can win. So that's the first one. We look at the second one. So that one failed. So if that had failed, it wasn't a win. It would branch to R2, which is our return address. Notice there's a NOP there. It's because skips 2 bytes, and branch R2 is only a 1 byte command. We've got to put another dummy byte in there for that to skip over. So the assembler understands NOP as being nothing there, and it'll actually put a 0 in. So we pad it out so the branch is in the right place. So if we've failed on finding anything on the first line, we're going to branch to what's in R2, which is return address, which is we set as RT1, so it's going to come back in here. So now we're going to do test line 2, which is byte 242, same test across there. But this time we'll be looking for D, E and F. And you notice the addresses we put into 240, 250 and 251 is do D, do E and do F. Here it was A, B and C, now we're doing D, E and F. And we're looking at the second byte in memory. And we do exactly the same tests. Coming through here again, looking for the same numbers, and branches down here, so it got branches down to D, E and F this time, if he wants to do 4, 5 and 6, which would be 4, 5, 6. And then when that's gone through, if that's failed, that'll be returning and return 2. So yeah, return 2 was put into R2, so return address is here. So we now do it again. Let's test the next line down, the bottom one. And this time we're going to be testing for G, H and I. And he does that again. If that fails, he'll come back to here, which is now going to test this vertical one. So we'll be wanting to test A, D and G. You notice we've got to move A, move D and move G into those addresses for setting. And again 244, which is this byte up here, being placed in there, and it does the same test again. And this time it would be doing, if it was found it was that one, it would be doing a do A. If it wasn't, it would be doing a D, do G. And if it was that one, it would be a D, do a G there. And it goes through all of them like that. So when it comes to 247, that's this one here, you'd be doing like A, E and I, which is A, E and I, be testing in that direction. And then the last one, it'll test in that direction to see if there's a winning move. If there isn't any winning moves, it'll jump to page 2 because there isn't enough room on page 1 to do any more. So it jumps to page 2. That's the simple bit of code for jumping to page 2. Here's page 2. There isn't any winning moves. So page 2 is looking to see if we need to block somewhere. Oh, we haven't won anything, so now we've got to check to make sure we don't lose. So this is very similar to the one before. We've got move 241, which is the first line, into R1, and then the return address here into 2. You notice the return is slightly different name. These ones were just RT. This one's got RTC on it. And you notice it's got a do AC and a do BC. Because they're slightly different, the assembler can't handle the same labels in different pages. Every label's got to be unique. So page 2 got labels and they've got to be different from page 1's, otherwise it will try and go to the address that's in page 1 and you'll be in page 2 and it'll get in a right mess. Rather than trying to write the assembler so we understood all this, I just create different labels. So it's exactly the same test as before. So this time we're looking to see if there's a losing place, as in, instead of testing for a 3, a 5 or a 6, we're going to be testing for a 24, a 40 and a 48. So here, if the player has gone and they've put a 0 there and they've put a 0 there, they'll have a 24 sitting in this byte. Because if they've gone there, then the CPU won't have gone into those two places. The code won't let you do it later on. So we've got to check to see whether that square, if these are two a set, is that square free for us to go in? So we check for a 24 over here, which says, yes, those two have been taken by the player. That means we need to go there, which is square A. So 249 is do A, little C on it to distinguish it from the others, so we've got do A. And there's do A, so we move 1 into R1 and go to page 3. It's got a C on there because it's go to page 3 here. Just the same as the previous page we was working on, but this time we're looking for places stop us from losing. Go through the code in exactly the same way, just looking for slightly different numbers just here. If we find a place we need to go to, we'll do it. And so here, if we've this branch to page 3C, we don't actually need that bit of code because we're only going down to here anyhow. We've set where we want to put our piece and we jump into page 3 again, which was here. So we're looking at this bit, do for a block. If we found where we need to block, we go to page C, which is place the cross and then test for a win. So he's on that bit for page 2. So if we find a block, we get out there. But if we failed to find anything here, we would have branched back with our return address and we would have gone for every possible option until we get to here where it says go to page 4, which is best move. So that's this one here, the best move. So we can't win, we don't need to block. Let's find a good place to go, which is page 4. We go down to page 4. There's page 4. So this is, let's say, best move. What you want is to take a square next to a place where you've already been. We get in the first memory address again, return address in R2, looking similar again. The addresses for doing A, B or C, this time they've got a B on the end instead of a C. Put them in our return, go to addresses if we're going to do those squares. We've got the return set up. Let's branch to test for the best. This here is a description of what it does. If we've got something in square C, it's this one here, then we're going to put it in B. If we've got something in B, we're going to put it in A. If there's something in A, we'll put it in C. So if you've only got the one, put it in one of the others. Bear in mind, that's where at the moment we're looking in this direction, A, B and C. We're going, we'll say A, B and C. When we're going in that direction, it will be A, D and G. And if we're coming in this way, it will be A, E and I. So it's trying to find a link. Go next to one we've already got. So this here is going to loop through 8 times. So it's 3 tests per 8, that's 24 tests. So test that way, that way, that way, that way, that way, that way, then that way, then that way. And find if we can go next to one of the squares we've already got. And it does that just by checking these numbers again, subtracting a number from it and seeing if it's there or not. So if we've got a 1, we're in A, put 1 in B here. It should be 250, 250B. There we go, do B, it's in 250. Subtract another one from it, so that's 2 taken away. So if we're in B, or if we're going downwards, it'd be D. If we're going anglewards, it'd be an E. If there's anything in that one, then do, it says a B, but it'd be like the second, whatever address is in 249. So in this case, it'd be a B, but if we was doing the next line down, it'd be an E. Oh, that makes sense. And then the next test here sees whether there's a 4 in there, because you've already taken away 2 there, taking another 2, that's 4. So this one's set, so do this one. Or if you're coming downwards and that one's set, do this one. Or if you're coming down here and that one's set, do this one. And this isn't A, B and C on here, although it says the letters here. It can be C, E, G, A, E, B, whatever's set here. This one is do the first square that's been set up beforehand. Second square on that one, that's the first square, and that's the last square. So it's whatever address has been put into that memory address here to go to. And if none of them fit, you just return from R2, which will be the next test down, until you come down to this one. If you got all the way down to here, it means you haven't found any to go to. Because if you have found one to go to, you've had your best move, you would have selected which one to do here, and branched off to place the cross on page 3. And because you haven't found one, you come down to here, you're going to branch to something called random, which if we look further down the page, is random, moves a 7 into 240, so go to page 7, and branch to start to get there. And what I could have done is those 2 lines of code, I could have just stuck them in there, branched to it, but that's the way it is at the moment. And let's look at random on page 7. So we haven't found anywhere to go yet, anywhere good. We go all the way down to page 7. So here we are on page 7, and we're coming at this point here. So in 3 to R1, let's read the random number that the motherboard creates and keeps in IO3. Puts that into R1, so we'll have a number between 1 and 9 in R1. So if we subtract a 1 from it, and it's a 0, then we know we must have had a 1. So we're going to skip to here. That's going to move the first byte, this one here, into R2. And then it's going to end it with 36, which means bits 2 and 5 will be shown through. So this is bit 2, and this is bit 5. So if that one is on, or that one is on, it won't be a 0. And it'll skip over, try the next one. But if it is okay, then it will do A. So, okay, that square is empty. Let's do that one. So do A, box D. Do A, box D. There we go. Move 1 into R1 and go to page 3 again, as in set that bit, which will be set that bit, place the cross in it, and go forwards. So if it's the square's not available, it branched down and tried 2. But of course, if we've got a 1 coming as a random number, subtracting 1 from it is just going to make it go negative. So that isn't going to work. That's going to fail, and they're going to keep failing, jump all the way through until you get down to 9. It's going to fail that as well, and it will branch to read random number, which is all the way back up here again. So what you do is you read the random number generator again. Well, hopefully it's updated by then, and it might be a number 2 this time. So come through. Is it a 1? No, it's not. So branch out to 2. Is it a 2? Yes, it is. Okay, we're doing line 241 again. We're going to test it against an 18 this time, which is a 16 and a 2. So that's that bit and that bit. Are they set? Or is one of them set? If one of them's set, then we can't use it. If not, we'll use that. If they're both off, we'll put it in B. So that will say do B. If not, try 3, which we know will fail because it was number 2 coming in. And it'll go all the way through again and then jump back up into here. And it will just keep reading the random numbers until one of them will fit. If it gets a random number that's correct but won't work, it'll come down here. So it will actually skipped over to this point here and it can't go through. It will branch to give up. This is what happens when there aren't any free squares. So it's tested all 9 squares to go in and there's none available. That means we've got a stalemate. And it will go to here where it will read the keyboard and it's just waiting for you to press the hash key, which is start a new game. So that's a stalemate, sits there. If it does find one, then it does one of these and puts the value into the relevant square, whichever one it finds available first. It will start from here and work its way through until it finds one. Well, it will start from wherever the random number said. So it could be starting here or here, but it would always go round in that order. So it's not totally random in that respect. So after we've done the set page, which is on page 3, it says we're back up to page 3 where it's going to put the move in. So this is page 3. This is where we're going to set our cross that we're putting in. You'll find out which one it is, set it all in, and then it will branch to test, see if we've won. So it tests to see if we've won. So move the first memory address 241 into R1, move the return address here into R2, and then branch to test, see if we win. Let's win 2. So subtract a 7 from it. If we've got the number 7 sitting in there, as in these 3 bits are set, then we'll have a 0, which means we've won. And that's a 7 we can do in that one, or any of them. So we're going to go through 241, 242, 43, test all of the memory addresses to see if there's a 7 in there. Because if there's a 7 in any of them, the CPU has won. So skips over to here. Yes, I've won. And the win here then just reads the keyboard, waiting for the hash key to be pressed. And when it is, it will branch back to the page 0 here and start again. If it hasn't won, it will return back and it will keep failing until it comes through to here and says, well, we haven't won, so let's go to page 5. It must be the player's go. So here we go, test for win. If we've won, you'll be down here. If you haven't won, we're going to go back up to here, which is the player's turn, which is on page 5. We're coming to page 5, clear the keyboard. We then read the keyboard. This is reading what the player is typing in, so we subtract a 1 from it, which is the A square. If we go back to here, if he's pressed a 1, it will be that key there. Well, actually it'd be that one, but yeah, top left square. If we've subtracted 1 and it's true, we get a skip 0, which moves down here, which is then gets this byte, 241. It then ends it with 36, which means we'll be testing this square here and this square here. Because we go to the next one down. Now that one and that one. So that's a 4, that's a 32, which is 36 in all. End it with 36. If we come out of a 0, then that square or that square is not, neither of those, that square isn't used by either the CPU or by the player. So you can go there. So it'll move a 32 into R1, then it'll add that to 241, 244, which is here, setting that A, so it sets an A there, sets an A there, and 247, so it's adding an A there. So that's 241, 242, 243, is filling all the A squares in. If this AND with 36 was false, as in this square or this one had been used already, it's not going to work. So it's going to branch the scan keyboard again. It's going to come back around here and just keep scanning the keyboard until you either drop out of here because you're not pressing the 1 key and you can go further through. Well, that's the only way out of it. So it just keeps scanning until you press some other key. So if you press, say, the 2 key, which is B, so take a 1 away, it's not 1, skip to the next key, subtract another 1. So is it a 2? Yes, it is. So skip over to here, get address 241 into R2. You need to test it to see whether this bit has been used or this bit has been used. So that's a 16 and a 2, that's 18. So you're going to AND it with an 18. If it's a 0, then it hasn't been used. Therefore, you can do a B, which is going to add a 16 to 241. So you're going to put that square in there, a B. And you're going to add 32 to 245. So you're going to put that one there. The B only occurs twice in this board, so you can set both B's are on. Because this B is for measuring down vertically, this one's for horizontally when you're doing your test. And you can say that would be finished with that, or if it's a 3, then you'd be looking for key C, which would be a 1 or an 8, which is 9. So we end with a 9 here, same thing. And if that's okay, then we move in an 8, or adding an 8 to 241. So we're adding an 8 there. And we're adding a 32 to 246. There we go, that's a C. That's this C here. And that's C as well. So we're claiming that square for the player. And once you've done that, whichever one it is, drops all the way out and does the test lose, which is this one here. So once you've placed your nought, you're going to test to see if you're lost or not, or if the CPU is lost. So that's on page 6. We go to page 6 for that. So here we are on page 6. We're coming at this point here. And we're going back to memory address 241 again. So get its value, put it into R1, save a return address into R2, then branch to test lose 2, which is, here we go, just here. So we're then going to subtract 56. So it's testing to see if the player has won. So like we had a test for 7 to see whether the CPU had won, we're now testing for 56. Because if we've got a 32, 16 and an 8 all on, add them all up, and that's 56. So if we've got all 3 of these on, then that's a winning line for the player. And we're going to test all 8 of those. So test it here, is it 56? If it's a 0, yes, then skip over, you've won. So we then scan the keyboard again for the hash key to start a new game. If not, we take the return address, which we put in R2, which for the first one will bring us in here. Then going to test byte 242. It's this one here. And then work its way down, testing each of these lines in turn. And each of these lines, as we saw, one's there, one's there, one's there, another one there, another one there, another one there, then that diagonal, and then that diagonal. So it'd be actually testing these bits up here on diagonals, and these ones down in the CPU. So these are the bits that are being tested for the player to win, all the red ones, and the green ones are tested to see if the CPU's won. So the same process, just a different number you're looking for. And if you didn't win, player didn't win, then go to page 1, which is all the way around again. So did I win? No, I didn't. So go back round into page 1 for the CPU to have its go. So here we go. Go to page 1, all the way back to the beginning. And that's it. That's how it works. I couldn't chop this into small blocks like I did on the BIOS, etc. I had to do it all in one go. But you could implement this Noughts and Crosses program in a different language or a different computer, whichever. I deliberately wrote it in a way that it can lose, because there's no point playing against a computer that you can never beat. So just add a bit of fun to it. You can beat it, and if you make a mistake, it will try and beat you. and really that was just a program to use to demonstrate how the CPU works. And you could program it to do pretty much anything you wanted. So that about rounds it up for the Build Your Own CPU series. I will be making some more videos. My next project will be to repair a Kim 1 single board computer. But to do that, I'll be needing a fast logic analyzer. I have got some that are 16 bits wide, but that's not enough bits. You may recall a little while ago I done a video on the 64 channel logic analyzer. Well, it wasn't much of a logic analyzer, it was very slow. I shall be attempting to build one that works at least 4 megahertz. I'll be using that to fix the Kim 1, which has got some various memory faults. I've done some preliminary tests, but I'll be starting from scratch and I'll be putting that into a new series. You can still come back for more videos. So don't forget to like and subscribe, and I hope to see you in the next video.